So, all right. So can you see this now? So before we discuss the energy and fuels, actually we'll no longer discuss energy and fuels today. Okay, it's like a reading material. So just check out eLearn. I'll upload the PDF of the PowerPoint on the different sources of energy and fuels. So we'll have a review on the concept, no? Essential concept in understanding energy. And this is on thermochemistry. So when we say thermochem, so we study the interaction of our material and then the energy, meaning matter and energy. So some materials would give us energy, some materials to undergo certain reactions will require energy. Okay, so this is our operational definition of energy and work. You're familiar with this in your physics, in your high school's Gen Chem. So energy, that's the capacity to do work. And then work is defined. One common definition is because a force acting on a certain distance. So we have the formula, remember? Force times distance. And between colliding objects or between two bodies, for example, energy can be exchanged. Okay, so collisions or any two bodies that would come in contact with each other. Okay, so I think you also know this classification of energy from the potential energy into the kinetic energy. So the energy of motion. Okay. Um, in kinetic energy, that is, if you notice, let's say when something is moved or a machine is moving, so you would really feel no, some kind of heat. So that's also that's thermal energy. So that's a product, no, when a potential is converted into kinetic energy. So it goes with it, thermal energy. When you collide, no, when you collide two objects, so you would by friction you would feel the heat, the thermal energy. Okay, so of course you also know this, the potential. This is the stored energy, as we all know. For chemical reactions, this refers to the stored energy in chemical bonds. So in our compound, so in the chemical bonds, that is potential energy because when it is broken, so the bond when it's broken, energy is released. And then also remember this, the law of thermodynamics, the first law, that energy cannot be created nor destroyed, meaning it's conserved. In other words, energy is just transformed. Also, energy is just transformed from one form to another. So it could be in the form of heat, light, sound, or a mechanical potential energy. Like here, when you place something on a spring and then when the spring moves, so that's converted into kinetic energy. All right. So these are in terms of application. So we have this other forms of energy, electrical. We convert that into electrical charge, flow of electrons, and then of course there's also heat associated with motion of our objects, and there's also light or radiant energy. So this depends on the energy transition. Remember the electrons, right? As the electrons proceed um, from low energy to higher energy, so that requires light. But when it falls back, relaxation from higher to lower energy level, it emits that energy that it absorbed. And then also nuclear in the previous topic. So we give a special emphasis on this because this is considered a clean source of energy. And this is potential energy because uh, we can harness this potential energy which reside in the nucleus of our atoms, meaning in the protons and in the neutrons of our atoms. And of course, in the bonds of our, in the structure, in the chemical bonds, that's also a stored potential energy. Okay, so I think you know this. Some units of energy, um, the kinetic energy is related to the mass and velocity. So it's a very familiar equation, no? 1/2 mv squared. And then that's if the mass is kilogram, and then the square velocity, that's m squared over s squared. So the unit is kilogram meter squared per second squared, and that is equivalent, no, to 1 joule. So 1 joule is the energy that is required to move 1 kilogram mass at a speed of 1 meter per second. Okay, and just to help us visualize the amount of energy. So this 0.10 kilowatt hour ng valve that's used for 1 hour, that generates or used up 3.6 times 10 to the power 5 joules. Okay, and then other conversions. So it's also converted into combination of Newton and meter, no? So kilogram meter square per second square. It's also equivalent to Newton a meter. Another common class, unit of energy, and usually we find this in food products, in the labels, that is in the form of calorie. So there's a difference. There's a small letter C, na calorie, cal, and there's the uppercase, na calorie. So the uppercase means 1,000 calories, the small lowercase, and then the 1 calorie that's equivalent to 4.184 joules. Okay, and then also you can this is familiar because atong kuryente sa balay is measured in terms of kilowatt hour. So 1 kilowatt hour, that's equivalent to this in terms of joules. Okay, so these are just visualizations. Okay, how much energy is used, no? By, let's say, to raise the temperature of 1 gram water by 1 Celsius, and then the bulb, and then when you run approximately 1 mile, that's how many kilometers? 1.6 kilometers. So you need to have this kind of energy to run, no, for 1.6 kilometers. It's just to visualize certain amounts of energy. So remember this. So we said in the first law of thermodynamics, energy is conserved, right? It just transformed. So energy is transformed from one form into another. Basically, the energy in what we call as our system. Okay, so this is the material or process we are studying. So the interaction with the surroundings. So the energy lost by the system is gained, no, by the surroundings, or vice versa. So when the system gains energy, it means it's the energy lost by the surroundings. Okay. So basically, that when you add all the energy, no, energy loss, energy gain of the system, of the surroundings, that corresponds to the energy of the universe, meaning everything, that's equal to zero. Because again, the energy gain of one thing or of one form is the energy lost of the other form. Okay. So we define this as the internal energy. This refers to the total energy. So when we say internal, both the kinetic and then the potential energy. And this is a state function class. So when we say state function, it depends only on the initial and final states, not on the process. So masipag magtuyok na siya, it does not matter. A state function depends only on the difference of the final state and then the initial state. Okay? Or the the products minus the reactants. So it's a mathematical concept. Okay? So internal energy is a state function. So here, again, just to illustrate the state function, so to go from the lowest point to the peak, so you can have different paths, right? So it will not depend on this, okay? But the state function depends only on the difference between here in the lowest point to the highest point, which is the peak, okay? So regardless of the path. So that's a state function. As we go along, and even if you remember, no, some of these state functions, thermodynamic properties, as we call them. Okay, and then again, the diagram shows the energy change. Okay, so energy can be added and energy can be removed. So if you go from the lowest or from the initial to the final state, then energy is added. But if you go down from initial, if you go down, that's energy is actually removed. Meaning if there's a decrease. So if there's a decrease in the internal energy, so energy is removed. And then if there's an increase in internal energy, that is delta E is positive. And then I think you also remember this, the energy flow in your system. So again, it's related to the surroundings. So if the system lose energy, that's a gain in the surroundings. So in other words, we have this working relationship between the two. So negative delta E of the system is just equal to the delta E of the surroundings. So if the energy flow is like this, no, from the system to the surroundings, it means that our delta E of the system is negative value, and then the surrounding is positive. So if you lose energy, that's negative. So if you gain energy, that's positive. All right. So the same thing, no? If it's the surroundings this time that would lose energy and the system accepts that energy, so delta E of the system is positive, and then delta E of the surrounding is negative. So the interaction between the system and then the surroundings. Okay? So this exchange of energy can be summarized by the interaction or relationship between the heat that's generated and then the work. Okay? So when we say heat, it refers to the thermal energy, meaning the system may either gains thermal energy, needs heat, or the system gives energy. So if the heat or Q is negative, it means that the system gives energy. And if the system gains, if the Q is negative, the system gives off energy. But if the Q is positive, it means the system gains energy. But for the work, if the work is negative, it means that the system releases energy by doing work. So that's the difference, no? So the system does work, that's why it releases energy. And if it's positive, it means that the system gains energy from work. Okay? So the Q and W are not state functions because it depends on the process. So it's not dependent on the initial and final. So it depends kung giinit ba siya, kung unsa yung reaction, kung unsa yung temperature. So it depends on the conditions, the Q and then the work. So these are not state functions. So the total energy or the internal energy is just the summation of the Q plus W. Okay, so again, the energy exchange, both the heat and the work. No? So this can be exchanged between the system and then the surroundings. Okay, so to illustrate the transfer also of kinetic energy, so in the billiard balls, so most of the kinetic energy is transferred. So when the two billiard balls collide, so most of it is transferred from the first ball to the second. And of course, there is certain amount of energy that is lost that is due to friction, the interaction. So the illustration here, so if you have around 5 joules as a potential or converted into kinetic energy, okay, when you hit the ball, the first ball, when it moves, it has this, let's say 5, it's a moving ball, 5 joules of kinetic energy. So that's basically most of it is transferred to the second ball. That's why it loses energy. It would stop eventually, but the second ball continues to move. So it's 4.5 joules. So around heat loss is 0.5. Okay, so that's when no the interaction. So to illustrate here the work here, because the system no performs work, so it's negative, and then that's why it releases energy. So negative. So the delta E overall is negative 5 joules. Okay, that's another illustration, but this time on a rough table. So that's the first one is on a smooth table. So most of the kinetic energy is basically lost through friction. Kaya rough mo kaya ang imong table. So energy is transferred no as heat loss to the table. And there's also heat exchange. Remember this concept. So when two objects, we can call them system and surroundings, so they can also exchange in terms of the heat. So occurs when system and surroundings have difference in temperature, meaning one is hotter, the other one is lower. One has higher temperature and the other one is lower temperature. So the heat exchange or the heat flow, it comes from the high temperature to the low temperature object until both objects will reach the same temperature. So that moment, we call it as thermal equilibrium. So you would know that no kanang mag-init ang tubig atong sagulan then sa bugnaw nga tubig kay kanang manghimasa ta no. So eventually it will reach thermal equilibrium. So in terms of the quantity, so when a system absorbs heat, of course, its temperature would rise, okay? And this increase in the temperature is proportional to the amount of heat absorbed, obviously. So this is expressed in the heat capacity, okay? The heat that is absorbed is equal to the, is expressed as a combination, no, dependent on the increase of the temperature plus a constant, which is the heat capacity. So the heat capacity represented by this uppercase C, the unit is joules per Celsius or joules per Kelvin. And the heat capacity depends on the objects, okay? For example, like our roofing, so depende no kung atong atop aluminum or a combination of metals. That's why we always do research to give us the best material, especially for the roofing, for example. So we should have very high heat capacity no, of the material. That's the ideal para it can absorb so much heat and would not pass through the roof. Okay. So these are some of the specific heat capacities of some of the materials, elements, some compounds, and then materials. That's why class, it's so refreshing. It feels so refreshing kung init yung panahon, yung mag-swimming pool dayon ta, no? Because look at the heat capacity of water. It's very high, 4.18. So it gives us that refreshing feeling. Okay, kung maligo tag if we take a shower or maligo sa swimming pool or sa beach because of the very high capacity of water. Okay. We look at the elements, no? So aluminum, 0.9 yung heat capacity. Okay? So dili po di lead, gold, silver, copper, gamay kay sila mga heat capacity. Samot kainit ang inyong atong feeling, no? Of course, these are also more expensive. Okay? So there is specific heat capacity and there's also molar heat capacity. It's just the difference is just very minimal, no? So when we say specific heat capacity, the symbol is CS. The unit is joules per gram Celsius. The heat capacity is joules per Celsius or joules per Kelvin. Ang specific is specific, no, to 1 gram of a substance. That's why it's called specific heat capacity. Specific to 1 gram of substance. What is the energy that is required to raise the temperature of a 1 gram of a substance by 1 degree Celsius? So that's specific heat. And there's also molar heat capacity. So instead of the grams, it's mole. The amount of heat that is required to raise the temperature of 1 mole of our substance by 1 degree Celsius. So heat capacity is general, and then specific heat capacity, and then the molar heat capacity. And this is intrinsic ability. Okay, it depends really on the nature of the material. So not on the amount of the material. So kung mas dagan ma-absorb. It really depends on its nature. So intrinsic ability. So it does not depend on the amount. It's the nature of the material, if it can absorb so much of heat or not. Okay, so when we quantify this, so we have this formula. Q, the heat, is just equal to the mass times the specific heat capacity and then the change in temperature. It's a very simple equation. I hope you remember this equation in quantifying our heat. So Q is just equal to mc delta T. So we have here a sample problem. How much heat is absorbed by a copper penny with a mass 3.10 grams, whose temperature rises from -8 to 37. So again, you can just follow the formula. Q is equal to mc delta T. Okay. So our delta T, our initial temperature is -8. So final minus initial. So 37 minus -8, that's 45. And then directly substitute. So when the mass is 3.10, the specific heat is given 0.385, and then times the change in temperature. So we get 53.7 joules. That is absorbed by the copper penny when its temperature changes. All right. Okay. Another important also concept is the pressure volume work, or the pressure volume combination. So the PV work is the work that is the result of a volume change against an external pressure. So in this piston, for example, so we can have a constant no external pressure. So if the system is doing work on the surroundings, work is negative. Okay, so we would measure the delta V. So for if the system is doing work on the surroundings, meaning the system, example here, when it, let's say there are some gases inside, no? So the system will push the piston, okay, from this point to here. So there is a change in the volume, okay? So that's the delta V, that's the expression of the work, Okay, so in here, the work is negative. It means that it's the system that does work to the surroundings. Okay, so as long as the pressure is kept constant, meaning the external pressure, let's say atmospheric pressure. Okay, so we always have this formula. So since work is negative, then we just transpose this. So work is equal to negative P delta V. Okay, so especially if you have gases in a certain container. Okay, so an example problem, if a balloon is inflated from 0.10 liter to 1.85 liters against the constant atmospheric pressure of 1 atm, how much work is done? So again, it's just a direct substitution to the formula, negative P delta V. So just change, calculate first the delta V, final volume, minus initial volume. So you should have a negative value. It means that it's the system that does work on the surroundings. Okay, so again, as a summary, so the exchange of energy between system and surroundings in terms of heat, we use the formula Q is equal to mc delta T. An exchange of work, we use the formula W is equal to P delta V. Okay, so how do we measure the energy at constant volume? So I think you'll have an experiment on calorimetry in the lab, no? So first, since delta E is again as what we have defined, is just equal to Q plus W. And then kung constant volume class, diba? Katong sa piston. So the work there is zero, right? So meaning wala man siya nag-move. Kung constant iyang volume, so there's no work. So work is equal to zero. So if this one is zero, it means that at constant volume, our energy, internal energy of the system is just equal to the heat. Okay? So in practice, it's not possible to observe the temperature changes of the individual chemicals involved in a reaction. So instead, we use an insulated, controlled surroundings and measure the temperature in it. Because, uh, of course, we don't see the chemical bonds, right? So to measure this energy, we can have a very simple setup. So we have a constant pressure calorimeter, and then this one, the constant volume calorimeter. It's called the bomb calorimeter. So which is usually made of sealed, insulated container filled with water. So basically, class, the bomb calorimeter can determine the energy, no, present, usually for combustion reaction. So when you burn something, how much energy is released. So it can be measured using the bomb calorimeter. So from our equation, the Q, or the heat of the surroundings, is just equal to the heat, no, in the calorimeter. Okay, so meaning when the system gives energy, if you have a reaction, for example, the reaction gives energy. So that energy lost by the system, that is the energy absorbed by the calorimeter. So in other words, if you monitor the change of heat in the calorimeter, you can also determine the energy that is released by the system or by a particular reaction. Okay, so and then remember our system, we can determine the change in the Q of our system by the simple formula, the heat capacity times change in temperature. Okay, so we can rearrange. So this is our working equation. So negative delta E of the reaction, because again, ganun negative din siya, because the system gives energy, is equal to the Q of our calorimeter, and that's equal to the heat capacity of the calorimeter times the change in the temperature. Okay, so this is how the bomb calorimeter looks like, no? So it used to measure the internal energy in a constant volume system. Okay, so a sample problem here is this one. So again, as what I've said earlier, the bomb calorimeter is usually used to determine the energy that is generated from a combustion reaction. So when a material burns, no, so obviously it releases energy. Kay mag-init man, di ba? Nag-init thermal energy. So we can determine the amount that is energy released using the bomb calorimeter. In the lab, I think either you'll have an experiment on the use of the bomb calorimeter, meaning constant volume calorimeter, or the constant pressure calorimeter. Okay, so let's have this sample problem. So when 1.010 gram of sugar is burned in a bomb calorimeter, the temperature rises from 24.92 into 28.33. So if the heat capacity of the calorimeter, which is 4.90 kilojoules per Celsius, so what's the energy for burning 1 mole? Okay. So again, we get first the C cal times delta T, and then the Q reaction is just equal to the negative Q cal because the reaction releases, and that's accepted by the calorimeter. Okay, so that's our working equation. So we have 1.010 grams of our sugar. Let's convert that into mole first. Okay, we get the mole. We get the temperature change, 3.41 Celsius. And then we use the Q is equal to C delta T. So we get 16.7. So the Q of the reaction is just equal to negative Q cal. So that's negative 16.7. Okay. So delta E is, because delta E, this one per mole. So Q of the reaction per mole of our sugar. So negative 16.7 divided by 2.5906 times 10 to the minus 3. It gives us negative 5.66 times 10 to the power of 3. So I can take note that any combustion reaction, ang delta E ana o ang Q is always negative because that's combustion. So when you burn something, it gives off energy. The reaction gives energy because there are bonds in the material, right? So these bonds are broken. So when these are broken, that releases energy. Okay. Another concept is the interaction of our internal energy of the system, but this time when the pressure is constant. No? So there is a thermodynamic property we call as enthalpy, the sum of the internal energy of the system and the product of pressure and volume. Okay, so internal energy plus PV plus work. Okay, so we can measure the enthalpy change of a reaction. So this is the heat evolved in a reaction at a constant pressure. So this one is a state function, meaning it depends on the initial and then the final states. Okay, so we also have a calorimeter for this to determine the enthalpy of reaction. So this is measured at constant pressure. So usually, delta H and delta E are similar in values. So the difference is largest for reactions that produce or use large quantities of gas. So, hindi sila magkapareha ang delta H and delta E. Kung if the reaction involves so much of gases. But usually, these are similar value. Okay? So we describe the exothermic reaction, endothermic reaction based on the delta H value. So when delta H is negative, that refers to an exothermic reaction, meaning the system releases energy. Okay? So ang exothermic tanawa, no? Like again combustion. So the fuel when it burns, it gives energy to the surroundings and heat. Okay? Pero if it's endothermic, so it's the other way around. It's the system that requires energy. Okay? So for example, the chemical cold packs contain ammonium nitrate that dissolves in water in an endothermic process. So that's why your hands get cold again because of this endothermic reaction. So katong liquid nga na ay ammonium nitrate, for it to undergo the process, mag-absorb siya energy from your hands. So there is some kind of a cooling effect, cooling sensation. Okay. So for the reaction, enthalpy of the reaction, the formula is just the summation, no, of the enthalpy values of the products minus the reactants. So let's say for this combustion reaction, it gives us this much of energy. So you can determine the energy per mole. So let's say per mole of our material, per mole of our C3H8, okay? Or for or per 5 moles of O2. So it depends on the equation. So example in this sample problem, how much heat is evolved in the complete combustion of 13.2 kilograms of C3H8. Again, just convert into mole, okay? And then evolved. Heat is evolved, meaning delta H is negative, okay? So you look at the term evolved, give off, released. These are synonymous terms, no, for exothermic reaction. How much heat is evolved? So that's exothermic reaction. Okay? So convert into mole and then 1 mole from the equation. From the equation, it gives us 2,044 kilojoules. Here, no? From the given. So if this reaction delta H is negative 2044, so what is the heat by 13.2 kilograms? So the 13.2 convert into mole, and then per 1 mole times negative 2044 kilojoules. Okay. This one. So there's an experiment. I think this is the experiment in the lab, the constant pressure calorimeter, either constant pressure calorimeter or the bomb calorimeter. So you can easily do this, no? So you just have you can improvise a calorimeter. You just have a nested foam cups. So there's a solution. So you have there the solution, the reaction, and then you have the solution. So the reaction will happen. So if the reaction would lose energy, so it will be accepted by the solution. That's why the expression Q is equal to negative Q solution, or negative MC delta T, because the reaction can possibly lose energy, and that's accepted by our solution inside. Okay, so this is a constant pressure calorimeter. So uh, in the experiment in the lab, so you have here a solution, actually it's just water, okay? And then you will hit a certain metal, you will drop a metal here, you will monitor the change in temperature at the metal before and after mixing, okay? And then you will determine the heat capacity of the metal. So that's in the lab. Okay, so we have this sample problem. So what is the enthalpy of the reaction per mole of magnesium for the reaction Mg plus 2HCl forming MgCl2 if 0.158 milligram reacts in 100 ml of solution that changes the temperature from 25.6 to 32.8 degrees Celsius. Okay, this is our general flow of the solution from the mass converted into kilojoules. Okay, so the given is 13.2 kilograms. So we convert into energy per mole, that's negative 6.12 kilojoules. Okay, so if you will have 0.158, if you'll have 0.158, this is for the previous problem. If it's 0.158, the same process, no? But you will use the MC delta T because there is now change in the temperature. Okay? So we convert first into mole, the 0.158, that's 6.4994, and then we get the delta T, and then we calculate the Q solution, MC delta T. So that's 3.0 times 10 to the power of 3. But remember, the reaction would emits energy, right? Because you would know, class, that the reaction would emit energy because the temperature changed from 25.6 to 32.8. So there's an increase in the temperature, meaning the reaction, meaning the Mg plus 2HCl gives you energy. So the expression Q reaction is equal to negative Q solution because you already have water. So when it reacts, the energy released by the reaction is accepted by the water. So the Q of the reaction now is negative 3.0 times 10 to the power of 3 joules. Okay, so if you have the delta H, if you have that Q, so you can easily solve the delta H of the reaction. So that's just the Q per mole. So negative 4.6 times 10 to the power of 5 joules per mole. Okay, and then relationships between enthalpy of reaction. If you multiply the equation, so of course you also remember this, enthalpy of reaction is extensive. So meaning kung mas daghan material, mas dako po ng energy, no? So meaning that the energy that is released depends on the amount. So enthalpy of reaction is extensive. So if you have our equation like this, no? It has an enthalpy of negative 390.5. So when you multiply everything by 2, so you now have 2 moles of carbon, the enthalpy is also multiplied by the same factor. Okay? If it's reversed, then the sign of delta H is also reversed. So if this is negative, so if you reverse, if it's CO2 to carbon plus O2, it's now positive. Okay? And a reaction can involve series of reactions. So the change in an enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So if a reaction proceeds in several steps, meaning the sum of the enthalpy changes in each of the steps, that is just equal to the enthalpy of the reaction, the overall. So this is what we call as the Hess law. So let's illustrate the Hess law. So for example, you are to calculate the enthalpy of this reaction. So these are the different steps. So what you'll do here, if you remember in your discussions in high school, you can rearrange, you can reverse the equation, you can multiply something, okay? But remember, if you reverse, the sign will be reversed. If you multiply the equation by a certain factor, the delta H is also multiplied by a certain factor, okay? So you need to rearrange the equations so that you come up with this. Of course, if you have species on opposite sides, they can be cancelled. And species on the same side, they are actually added. Okay? So, in the first equation, what do we do in the first equation? We multiply by 1.5. Okay? Because in the final equation, the NO2 is in the reactant, right? In the first step, no, in the first equation, the NO2 is in the product. So it means that we need to reverse it, okay? That's why it's now positive. We don't just reverse, we also multiply by 1.5 because we wanted to have 3. The coefficient of NO2 is 3, okay? So the coefficient of NO2 is 3, so that's 3 times 1, I meaning 2, then times 1.5 it is 3. So we just did not reverse it, but also multiplied by the same factor. For the second one, our nitrogen, obviously, we don't have nitrogen here, okay? So obviously, it must be cancelled. So what's our basis if this second equation will be reversed or not? Look at the third. The third equation has NO, and in the final equation, NO is on the right. So in other words, this third step or equation must be retained. So the second, and since we don't have nitrogen here, the nitrogen must be eliminated. So in other words, the second step must be reversed para ma-eliminate or ma-cancel. So here, um, the the coefficients also is multiplied, no, by 0.5 so that we can cancel. Okay. Sorry. It's the third equation that is reversed. The second equation is not reversed because again, if you look at the equation, the second equation is not reversed because of the nitric acid HNO3. HNO3 is in the product side in the overall equation. So this must be retained, but we multiply 0.5 so that we get the desired coefficients. And then for the third equation, we simply reverse it. Okay? So when you add the equations, so 1.5 times 2, same, no? Distribute. And 0.5 distribute. So when you add the 3 equations, this will give you this. So actually, para mas klaro, no? So let's use okay. So sorry. Alright, so para mas klaro, so you distribute this, no? So 1.5 times 2. So we have 3 NO2 forming forming 3NO plus 1.5 O2. And the second equation multiplied by 0.5. So 0.5 times 2, that is 1 and 2 plus 0.5 times 5, that's 2.5 O2 plus 0.5 times 2, that's this is N2 plus 2.5 O2 plus 0.5 times 2, that's water, and then 0.5 times 4, that's 2 HNO2. Okay, and in the third, there's no multiplier, 2NO 2NO forming N2 plus O2. So you cancel. So you cancel N2, N2, as well as what else is canceled? O2, 1 plus 1.5, that is 2.5. That's 2.5. Okay. And then NO. So this 2NO is cancelled. But in the right, that's 3. So minus 2, that's 1. So the remaining equation now is 3NO2 plus water forming 2HNO3 plus NO. Okay? So, and then the delta H, you just add all the delta H values. So that gives you negative 49 kilojoules. So that's the SS law. Okay? And then we also have what we call a standard state. So when we say standard state, this is just the state of any material at a defined set of conditions. So in terms of pressure and in terms of temperature and in terms of concentration. So when we say standard state, the pressure is 1 atm, and then the temperature is 25 degrees Celsius for pure solid or liquid. And if it's a solution, the concentration is 1 molar. So when we say standard enthalpy of change, so this is the condition that we mean. Okay? And there's also the standard enthalpy of formation. So basically, the enthalpy of reaction or enthalpy change, no? Enthalpy of reaction is just equal to the summation of the enthalpy of the products minus the enthalpy of our reactants. And then ang formation, the enthalpy of formation, so you would have this symbol, kani? It means standard, no? The degree. So that's standard. It means standard. Standard enthalpy change or standard enthalpy of reaction or standard enthalpy of formation. So the formation is, it's of course a reaction, but how do you form a compound from its constituent elements? Okay, so when the formation, for example, of water. Okay, so how do you form water? So that's coming from the hydrogen and oxygen. Okay, so hydrogen and oxygen. The enthalpy of formation of the pure element in its standard state. Example lang, hydrogen, O2, H2. So by definition, that is 0. So to illustrate the formation equation, we should have the thermodynamic table. It's actually given. Okay. So reaction of elements in their standard state to form 1 mole of pure compound. Meaning, so kung hydrogen, kung water, H2 plus O2 forming 2 water. or that's 2, 2H2 plus 1 O2. So this will be our equation. Okay, so when you write, so based on its element form or natural form. So if you form carbon monoxide, so it should come from carbon. The most common isotope of carbon is graphite. And in the natural form of oxygen, standard state is O2 gas. Okay? And then of course you balance the equation. So that's how you write the formation reaction, no, for carbon monoxide. So when you calculate for the enthalpy change for the reaction, as what I've said, it's just the summation, the difference in the enthalpy of formation of the products minus enthalpy of formation of the reactants. So I think you remember this, no? Let's have a sample problem. So calculate the enthalpy change in the reaction. So first, you write the formation reactions for each of the compound. Okay, that one. And you can have this one, these are constant values from thermodynamic table. Okay, so these are given. And then you arrange equations. So you have this enthalpy of formation. So you get this again from the table, no? Formation of the C2H2, of CO2, of water. Ang O2, that is zero. It's standard state, natural form. So that is zero. Okay? And then you arrange equations so that they add up the desired reaction. Okay? So this one, no? So if you in the problem, in the equation, you have 2C2H2. So the C2H2 here is the formation is 227.4. So since the coefficient of C2H2 is 2, so you multiply its formation. So 2 times negative 227.4. We have 4 carbon dioxide times its enthalpy of formation. The same thing with water. So 2 times the enthalpy of formation of water. Okay? So we get the answer negative 2600. Okay? For overall. Or you can use this formula. So this one you can just rearrange, no? Which is just like Hess law. So you can solve this using Hess law. Or you can just use this um, equation. Enthalpy of reaction is just equal to the enthalpy of formation of the products, the sum, minus the sum of the enthalpy of formation of your reactants. Okay? So 4 times CO2 plus 2 water minus 2 C2H2 plus 5 O2. But this one is 0. Okay? Then just substitute. So you still get the same answer. Okay? So we have a problem here. How many kilogram of octane must be uh, combusted to supply 1.0 times 10 to the power of 11 kilojoules of energy? So this is the solution. Okay, from the formula, so uh, you look up these values from the table. So this is given. So to no need to look for this, no? So in the exam or in the assignment, so these values will be given. Okay, so um, again, direct substitution. Enthalpy of the reaction is enthalpy of the products minus reactants. Okay, and then since you have this enthalpy of reaction negative 50, negative 5074.1 kilojoules. The question is how many kilograms if you have this much of energy. So again, it's just ratio and proportion in a way. So if the octane would give you this kind of energy, so that's negative, and times our enthalpy of reaction, it's negative 5074 per 1 mole, so cancel, cancel, and then convert into kilograms. So um, if we want to have this kind of energy, we need to have how many million, 6 zeros, 2.3 million kilograms of our octane if you want to supply this kind of energy. Okay, so that's the end of our discussion or quick review on the thermochemistry.